Okay, good morning, everyone. Outside there, guys, we are starting. Good morning. So it's my pleasure to introduce Souvik, who is a fellow here this year, and he will give us a review of how to model sparse random graphs to see when they have large connected components and things like that. So with that, I don't want to take your time away. If you are online, please shout your questions. We will not monitor them sort of in the chat, but just you have to speak up and ask your question. And I assume here we do the same thing as during all the lectures. Please ask him questions as soon as you don't understand something. And I sometimes will also ask questions whether I understand it or not.
Sure, thank you. All right, let's get started, and thanks for coming. And let me start by thanking Christian, Jennifer, Nicole, and Amin for organizing this workshop and also asking me to give this tutorial on random graphs. So I will be talking about sparse random graphs. Sparse means the average degree on this type of graphs will scale, not scale, the average degree will remain bounded. Okay. So the number of edges in the network will scale linearly with the network size. It turns out that the techniques to deal with sparse random graphs are quite different than the techniques to deal with dense random graphs, for example, or dense graphs in general, as Christian talked about. So I would like to introduce different models of sparse random graphs, and along with it, I would like to also give you some glimpse of these techniques that we use to deal with sparse random graphs, okay? And to restate Christian's message, if you have any questions in between, please stop me, okay? So let's get started with a few questions that we are interested in this workshop. How does a disease spreading through a population become an epidemic? What can cause communication networks, such as internet, to break down? When does misinformation reach a large amount of people? So at first sight, these questions may seem unrelated, but there are some commonalities here. First of all, there is an underlying network in all these examples, which is really large, containing millions and often billions of nodes. And there is a really complex structure that is connecting these nodes. And number two, there is something happening in these networks which has drastic impact on the network, right? So if we're looking at the epidemic, it can either stay contained in a small region, or it can blow out or infect a lot of people. So this type of behavior that has drastic impact on graphs is kind of called a phase transition phenomena. And random graphs provide, quote unquote, simplified probabilistic representation to model this type of complex systems, okay? The probabilistic representation is such that it captures structural properties of the network, such as the heterogeneous degree distribution that occur in networks, also things like community structure. And also random graphs are designed to provide the type of phenomena that we observe in real world. For example, types of behavior like phase transition. Okay, so random graphs satisfies both these purposes. So why are random graphs useful? Why study them at all? Well, first of all, random graphs are good graphs in some sense. General graphs are usually too messy. It's very hard to deal with that. You can always find counterexamples if you are dealing with general graphs. But random graph is kind of a way to pose regularity properties on networks. For example, random graphs has nice property like expansion, and also Christian will be talking about a lot of notions of convergence, right? And random graphs usually have these convergence properties as well. Okay, so in this sense, random graphs are good graphs, first of all. And number two is often random graphs reveal the core properties that are responsible for our phenomena of interest. This may seem vague at first, but this is the theme we will focus on actually. The example we'll be considering is to see how local neighborhood structure of random graphs influence global properties like this phase transition, emergence of large components, or distances in the graph. Okay. And finally, in CS, random graphs serve as a good ground to get provable guarantees of heuristic algorithms. For example, there are many NP-hard problems such as graph partitioning and coloring, and usually when one comes up with heuristic algorithm, one tries to first verify them on random graphs. This third theme I will not go into at all. I will stay on the second theme most of the times. Okay, so here is our plan today. Today, I will mainly focus on one technique called local branching process approximation on random graphs. We will understand this technique on a very simple probabilistic model called Erdős-Rényi random graph, which you might have heard about already, and explore this technique and its relation to the giant component problem on Erdős-Rényi random graph. Okay, so once we set up the techniques and sort of get a sense of what are the high-level steps, after that we will apply this technique to more and more complex models. So this part I will do in detail. So tomorrow coming up is percolation relation to epidemics on networks as well. I'll talk about that. And also, if there is time, I will talk about a very nice technique that uses stochastic process convergence to deduce properties of random graphs. Okay, so that's the plan. Let's get started with the most elementary, yet I would say most fundamental model of random graph, Erdős-Rényi random graph. Right? So we are given n nodes, say labeled 1 to n here, and the model is simple. Each edge in the graph appears with probability p independently. So at the end, we end up with a random subgraph of the complete graph. Throughout, I will use this notation ERNP to denote Erdős-Rényi random graph on n vertices, and p is the probability. Okay. Now, although this model is called Erdős-Rényi random graph, this model was actually studied by Gilbert in 1959 mathematically and also heuristically by Solomonov and Rapoport in biology. So Erdős and Rényi in 1959 worked with a slightly different model where usually one would choose these edges uniformly at random instead of keeping them independently with probability p. However, in a sequence of like 8 papers or so on, they laid the foundation of the modern random graph theory we know today. Okay, so that's why I think even this random graph model is rightly called the Erdős-Rényi random graph model in the literature. Okay, so
can I make a small obnoxious? There's a sociologist, Marino, who in 1938 was computing probability of isolates in basically an ER graph.
Okay,
it has a corollary of sociometry. So there's even older.
Okay, I see. I didn't know.
Sociologists can lay the claim to the.
So it was in 1938.
38.
Okay, thank you for the comment. Okay, so what are we after? We are looking at Erdős-Rényi random graph where the network becomes really large. Let's say we take an Erdős-Rényi random graph with n equals 1000. Now we see something is happening when we go from p equals 0.5 over n to p equals say 2 over n. So on the picture on the left, you can see all the components are really small. They are microscopic components, right? And on the right, you see there is a huge component that gobbles up most of the vertices in the network. And there is only one large component that gobbles up most of the vertices. There are no two large components, right? That's very important. So you will see actually the same behavior or same type of pictures if you even saw put p equals 0.9 over n here and p equals 1.1 over n on the right. Okay, you will see kind of the same pictures. So the results we are after is if p equals lambda over n, then there is a phase transition around lambda equals 1. Think of lambda as the average degree of people in the network. Okay, so it is just saying that if the average degree in the graph is less than 1, then all components are small, microscopic. You see this picture. And if the average degree is more than 1, there is a unique giant component. There is only one giant component. Yes, please.
Average degree is 2 lambda, right?
No. Degree is lambda. We have potentially n minus 1 neighbors each. That is with the problem
P equals
p,
1 over
so
n, not
p times n.
The average degree is
Average
2
degree
lambda.
is lambda.
No.
Q times n.
Each edge has 2 nodes that touches.
So let's say if you look at, say, the degree of one vertex.
Yeah.
So it has a binomial many connections, right? What is the binomial? It is binomial n minus 1 p. So the expectation is n times p, n minus 1 times p.
Okay.
Right? So p equals lambda over n.
The number of edges, it's n lambda over 2.
Yes.
That's the 2.
Yes, expected number of edges about edges
That's
2
a
times
factor
p.
of 2 between if you fix the number of edges or fix p.
Okay, sorry, never mind. Sorry.
Yeah. So we are trying to find component sizes, right? What do we do when we try to compute component sizes? We run some exploration algorithm like breadth first search, for example. And when the breadth first search ends, at that moment we have found the component, and then we know the size of the component, right? We'll do exactly same on the Erdős-Rényi lambda. We do breadth first exploration starting from, say, an arbitrary node, node 1. Okay. So this is how the breadth first exploration will look probably. In the first step, how many neighbors will it have? I just said it will have binomial n minus 1 lambda over n many neighbors, right? So in the first step of the breadth first exploration, this many neighbors will be explored. How many neighbors will be explored in the second step? Can anyone tell me? How many? So what is the distribution of the number of nodes that you get in the second step from each node?
4.
Exactly. Thank you. So this is binomial n minus 4 because 4 vertices have been explored. We have n minus 4 unexplored, right? And we can generalize this argument. So in general, let's say Si is the number of vertices explored up to time I. So n minus Si is the number of unexplored vertices. Then each of the vertices at depth I will produce binomial n minus Si and lambda n many new vertices in the next step, right? So now we know how many things are produced in the next step, but there is one problem when we sure.
So if I look at the first vertex, I agree that this is n I minus 4 lambda over n. But if you look at the next one on that same level, you actually have n minus 7 because you're not allowed to. So this formula is not quite correct. But it's not. It's only the first one in generation I which has this.
Let's make it precise. So I say that conditioning on whatever has happened up to depth I, what is the distribution of each of the things that what are the distribution of them? That is always binomial n minus 1. So you all only condition on up to this point.
But they're not independent.
Then they are not independent. Thank you for the clarification, Christian. So Oh, there are, first of all, two obstacles to analyze this process. Number one is we see that this number of unexplored vertices is depleting, right, over time. So there is a depletion of vertices that makes analyzing this process challenging. And number two is there can be conflicts, right? So it can be that there are vertices which connect to, say, two vertices in the previous generation. It can happen in a graph.
To be precise, returning to Christian's answer, question, indeed, is you are describing the so-called upper coupling.
I have not described the upper coupling.
But I think if you're writing this fashion, then I think as Christian pointed out, it's kind of upper coupling that you are working with, but that's fine. Approximately all the same. Although you didn't describe it that way, because you are looking only at the depth.
Precise, so maybe the typo is instead of that height should be a step height.
Step height will be perfect, but that's why something.
Yeah, but I didn't.
Yeah, I did not write out like the sigma algebra and so on. So we are always conditioning on whatever is happening up to wall of radius I, say, starting from the word. Okay, so there are two problems, depletion and conflicts. Let's get rid of these things. And so let's consider a random process that does not have any depletion, neither does it have a conflict, right? So in this case, we have binomial n lambda n many neighbors in the next generation always. And similarly, it continues in the next generations as well. So the object that you see on the right, where each vertex produces binomial n lambda over n many vertices in the next step, is called a branching process. We will be using branching processes a lot in the proof. Okay, but now we see a very simple fact. The fact is, let nk be the number of vertices at depth k for the Erdős-Rényi exploration, and nk bar is the number of vertices for the branching process. So we see this simple fact that number of things we have in the exploration is less than equal to number of things we have in the branching process. Okay, let me write this because I will use it a lot. Nk yeah, it is a big N. Nk, and there is nk bar, which is the same thing for the branching process, right? And we know nk is less than equal to nk. Good. Now, just using this fact, we can say why the component sizes are small if lambda is less than 1. Just using this simple fact. Why? Let's say C1 is the component size of vertex 1. And let's try to just compute the expected component size of vertex 1. Well, this is equal to the sum over the things that we find in breadth first exploration is in each of the steps. So we sum over everything and take expectation. But now, using our nice fact, we can bound nk by nk bar, the number of things that are produced in the branching process. So we are left to calculate the expectation of nk bar. What is the number of things we get from branching process, right? So let's do a simple calculation. We will try to show for a branching process, this number is lambda to the power k. It is decaying geometrically. So suppose we condition on the previous generation, right? So you have nk minus 1 bar in the previous generation, and each of them is producing binomial n lambda over n. So this is the expectation will be n times lambda over n, but we have nk minus 1 bar many in the previous generation. So it is equal to expected number of things we see in the next generation is equal to this quantity. So expectation of nk bar equals, these things cancel, lambda times expectation of nk minus 1 bar. And now you see what is happening. We can iterate this equation again and again to arrive at this expectation is decaying geometrically, right? It's decaying like lambda to the power k. So since lambda less than 1, we can sum over this, and we have the expected component size is less than equal to 1 over 1 minus lambda. So what have we shown? We have shown that if lambda is less than 1, then the branching process has size O1, and therefore the expected component sizes, which is upper bounded by the size of the branching process, that is also capital O of 1, right? So this is showing that if lambda is less than 1, all the component sizes are small. Of course, in order to prove it for all components, you have to think of maximum, right? You have to get uniform guarantees on the component sizes. So let's state this result. So if lambda is less than 1, then the maximum component size decays like logarithm of n. So if you divide by n, it converges to this quantity I lambda. There is no prime here. That's a typo. So it kind of makes sense because the branching process progeny is decaying exponentially, right? So maximum is log n, but this maximum, the CUs are not really independent, so one has to be careful while doing the analysis. Okay, I will not prove it. Okay, I just wanted to mention this result. But if you are interested in the proof uses large deviation estimates for branching processes, and you might notice that this is actually related to large deviation rate functions, right? So it's the large deviation rate function for a Poisson random variables. So you can use large deviation to get more precise estimates on the tail probability that component size is more than some number t. Okay. Okay. Next up, lambda more than 1. First, let's again look at our branching process. What does the branching process do? Well, from now, we will do a simplification. Instead of considering binomial n lambda over n progeny, we will consider Poisson lambda many progeny. They are approximately same, right? By limit theorem of binomial distribution. So at each step, this branching process will produce Poisson lambda from now on instead of binomials. Now, there is a classical fact in branching processes that says if lambda is more than 1, so the average number of children produced in each generation, if that is more than 1, then the branching process will survive up to infinitely many generations, and this probability is positive. It stays bounded away from 0. Okay. You can even calculate this probability using this fixed point equation. So let me just tell you why this arises. This 1 minus zeta equals to e to the power minus lambda zeta. Well, 1 minus zeta lambda is the probability that the branching process does not survive, right? So it's the probability that branching process dies out. But if the branching process dies out, then all of it's for all neighbors also die out. If the branching process is not infinity, the original branching process, none of its neighbors can survive. But now, let's say we have x many neighbors. So then this probability is equal to, let's just write the equation. This is equal to 1 minus zeta lambda, because each of these are also Poisson branching processes, right? So, and none of them will survive. So 1 minus zeta lambda to the power x, right? Because we have x many projects. We can take the expectation of this, but x is a Poisson random variable. We can calculate the probability generating function of Poisson random variables, and you get e to the power minus lambda zeta from there.
You just plug in the probability generating function with the parameter 1 minus rho lambda, isn't it? It's a sum over all possible number of subtrees. Let's say L, then it's sum of all possible L over the probability that Poisson lambda is equal to L times 1 minus your survival probability to the power L, because all the subtrees should die out. But if you take the expectation, no, there will be one parameter, extra parameter. If you take the expectation, it's L times then. It will be L1 parameter. It's a derivative of the PGF.
No, if you have k neighbors, then all of them have to die out after.
No, if you take the expectation, it will be derivative of the PGF, not the evaluation of the PGF. There will be one factor of.
No, if we write this out, this is sum over L, lambda to the L over L factorial, 1 minus e lambda to the L, which is e to the minus lambda.
Oh, I did the wrong calculation. You're right. You're right. Now it's it. Yeah, you're right.
Okay, so this is how you can also calculate the survival probability of the branching process. And if lambda equals lambda more than 1, then there is actually always a unique positive solution to this equation, and that corresponds to our branching process survival probability.
You want to draw the picture for us, convincing us that lambda equals 1 is a critical point?
What do you mean?
Just draw e to the minus lambda, draw the function e to the minus lambda zeta and the function 1 minus lambda. Convince us that it's based on this.
Okay, so this behaves like this, right? And if I draw it correctly, yes, it becomes plus, and
the derivative is lambda.
And so there is only one solution, right?
Wait, it starts at 1.
Lambda equal to 0 is always a solution.
They both start at 1.
That both start at 1.
It's 0, so you're drawing the different.
Zeta equals 0 is always a solution.
Oh, so if I have 1 minus beta, so draw it. So beta equals 0, it is 0. Beta equals 0, it is 1. The left hand side, and the left hand side, you get this one. And on the right hand side, there is
larger than 1, smaller than 1, it doesn't intersect.
Yeah. So there is a point of intersection. Thank you, Christian. Okay. Now back to Erdős-Rényi and algebra. So we now know that the branching process will survive up to infinitely many generations. But the whole point of the argument that we will see coming next is the exploration. The branching process is not only an upper bound to the exploration, it follows the exploration follows the branching process very closely. So they grow together. Therefore, if the branching process survives, the exploration continues for a long time. And if that happens, that gives rise to a large component. Okay, that's sort of the intuition. So a component is large with some probability zeta lambda, say, right? So in the beginning, you can do even some back of the envelope calculations, like number of vertices that are in large components is approximately n zeta lambda. So n zeta lambda is the number of vertices that are in large components. But from this, it's not clear how many large components are there, and also what does large mean, right? So there could be that there are two components of size n zeta lambda over 2, or square root n many components of size square root n. But that is not the case. and we have this result. So let Ci be the ith largest component of Erdős-Rényi random graph. Let's write this notation because we'll use it. Ci is the ith largest component. So don't get it confused with C bracket U that we saw, right? Let's write C bracket V because this is the size. This is size and this is the component size containing V. So this is saying that if we look at the largest component, the proportion of vertices in the largest component is approximately equal to zeta lambda, and there is only one giant component. The second largest component is small compared to the largest component. So as I promised, we'll see that a unique giant emerges for Erdős-Rényi random graph, right? Okay, we will prove it. So the main idea is to get bounds on moments of large component sizes. So we will mainly prove two lemmas. The first lemma concerns the proportion of vertices in components of size greater than equal to L. Okay, so this sum, if you forget about it, this sum is the total number of vertices that are inside components of size greater than equal to L, and the quantity on the left is just the proportion of vertices. And I claim this proportion is approximately equal to our zeta lambda plus a smaller correction. The correction goes to 0 if we grow n to infinity and then L to infinity. Okay, if we take n and L large, we will get this result. So in a sense, this is the first moment of the distribution of component sizes. Good. We'll also show the second moment of the component size distribution of large components that converges to zeta lambda squared, the square of this quantity. Now I claim that the proof just follows very easily.
What's your notation? O, L, N of 1.
Oh.
So you need some order, right? N goes to infinity first, then L goes to infinity,
yes.
Or does L not go to infinity? How should I see?
So x n L equals small o n L1 means probability that x n L is more than epsilon lim sup n tends to infinity limit L tends to infinity equals 0 for all epsilon positive. That's the rigorous way to think about it. OLN. Yeah, this OLN.
Souvik,
Yes.
isn't this typically L depending on the n, like over the entry to third?
You don't need it.
You don't need it?
No. So the proof that I'll be doing is from this book, Random Graphs and Complex Networks, Volume 2. And for
So you
this,
don't do this no middle ground business at all?
yes, I will do that. But for that, you actually don't need to for L to grow with it.
Thanks.
So the whole idea is we want to set up a proof that will work for other random graph models. It should not specialize to Erdős-Rényi random graphs. We will try to find conditions under which these two lemmas can be verified very easily. Well, now I claim that from this, the proof follows very easily. Why is that? Let's say xi equals our ci over n indicator ci is greater than equal to L, right? So the condition is just saying that sum over xi is approximately equal to zeta lambda and sum over xi squared is approximately equal to zeta lambda squared. But then, well, approximations can be made precise using epsilon delta arguments, so we'll not go there. So that implies sum over xi xj I not equal to j, the cross product terms. So we can take a square here, right? So we know that the cross product terms will be approximately 0. So it cannot be that two of the terms are positive. If that is the case, then cross product won't be 0. So only one of them can be positive. And since the sum is zeta lambda, that one will be zeta lambda. So this shows that the large component sizes, proportion of vertices in that, is approximately equal to zeta lambda. And the second largest component has a negligible proportion.
So that means that if you want to prove that you effectively need to calculate force moment, because to prove that with high probability the second moment behaves like that, you have to eventually control the force moment. All right?
No, so we'll see when we get there what we actually need. Okay. So this completes our proof of existence and uniqueness of the giant. Are there any questions up to this point? Because now I will dive into the proof of these two lemmas. Any questions?
Sorry, just repeat the argument. So you take the square of the equation in lemma 1 and say that the cross products are 0.
Yes. And there is a way to compute this cross product. I will show you.
Which is a separate matter not covered by the lemmas.
No. Okay. So next we.
So wait. Just due to this question, do the lemmas just imply it, or do you need another lemma to control the cross?
Well, I mean, you could have written this lemma in terms of cross product. That's what exactly we'll actually show. But I just wrote it.
So these two lemmas don't quite imply it. You need the more or less they imply it, but not really. Or
So they imply that cross product terms go to 0, and the cross product term is going to 0. That is something we will be verifying for it.
I still don't understand the logic. So these two imply the cross products go to 0, which then implies that you have a unique giant, right? So the lemmas, so this is not a separate thing. These two are.
Yes, these two are.
So what was your remark supposed to mean?
Oh no, I misunderstood what he said. So it isn't. I just don't. I don't immediately see how the. So your claim is the second lemma implies the cross product.
Yeah.
Got it.
Well, the second lemma implies the cross product. I used it for this argument, right? So actually, what turns out to be important. So I wrote this here in terms of like a second moment condition that looks nice, but actually what you need to verify is this condition. The product is 0, and we'll verify that condition. So this is just convenience.
Lemma 2 is an implication of this condition.
Yeah, of this cross product.
You will prove the cross product is 0, and therefore the second moment is square.
Well, if you know this first moment lemma, then cross product is 0 if and only if sum of squares is 0. So that's an equivalent statement. So I have written one of the equivalent statements. Okay. So next we will prove the two lemmas, but before that we need to set up something. Remember, we said that the whole point of this argument would be to show that the exploration grows together with the branching process. So the exploration is approximately equal to the branching process. Okay. So let's set up that tool. So we will show that nk is approximately equal to nk bar. So nk and nk bar are the number of vertices at depth k for exploration and branching process. And this approximation stays true until we have explored s many vertices, where s equals n to the power a, where a is less than 1 to be precise. But it is saying as long as you have not explored a proportion of vertices, a positive proportion of vertices, until that, the branching process and the exploration process grows together always. Okay. So in order to prove this approximation, remember that there were two sources of discrepancy, right? The first source was the depletion of vertices, but we can deal with depletions quite easily. Well, binomial n minus s if s equals small o of n, the approximation that we have Poisson lambda, the many neighbors explode in each step, that still remains true always. Okay, so the depletion does not matter too much. What about conflicts? Remember, conflicts are things where
I actually have a question on your depletion. Since you argue this thing generation by generation, it's less clear to me how this depletion works, because while the first one you sort of, for the first one you know that you use the number of vertices from the last step. If you do a whole generation, how do you know that you don't actually, when you do the last of your exploration,
you're right.
any of them?
So you need some uniformity conditions. So I cheated there. I agree with you.
So just for me, how do you deal with that?
So I think you can come up with some concentration type arguments here to deal with that. Because as long as S equals say small o of 1, then this approximation is true uniformly. But when it starts growing, then you concentration kicks in. Right? Because you have explored a lot of vertices, then the branching process starts growing exponentially.
What do you mean by concentration? What concentration?
So the expected, the number of vertices you produce in the next generation tends to concentrate if you have survived up to a long generation of it. I will talk about it in a moment.
So what he's saying is, once I have a lot of vertices in generation T, then the generation T plus 1 is the sum of many random variables. It's therefore concentrated. But they're not independent anymore, and so I still don't buy your concentration. Because then,
yes, they are not independent, but the coupling stays true.
I think he's using the upper coupling, therefore he has always this binomial lambda, n lambda or Poisson lambda as an upper coupling, and then you use Chernoff, I think, for the concentration.
Okay.
No?
Yeah.
this is a traditional one uses lower couplings, but that only works if you do explore vertex by vertex, and you do generation by generation, for which the lower couplings don't work.
So you can do the lower coupling, right? So here, I mean, we will only use this fact until S equals like square root n. So you can always do the lower coupling by subtracting S equals square root n.
We do it offline.
Okay. So what about, let's try to compute the number of conflicts, right? I claim the expected number of conflicts is some constant times lambda to the power 2k over n. Now, why is that? Let's say, suppose you are in the k minus 1th generation, until which you have explored sk minus 1 many vertices. So outside there will be n minus sk minus 1 vertices, right? And each of them are candidates of producing a conflict. Now, a conflict occurs if this vertex connects to 2 vertices in the previous generation, which happens with probability lambda square over n squared. So the expected number of conflicts is less than equal to expectation of say n minus sk minus 1 times lambda square over n squared. So you have taken care of all the possibilities here, and also you have to take care of all possibilities here as well. So there are at most nk minus 1 squared choices in the previous generation. Okay. Well, we can do a few more steps. Let's replace upper bound this by n. So we get lambda squared over n, expectation of nk minus 1 squared. Again, as we did the expectation calculation, we can do the expectation calculation. Okay, so let me do another step. So this is less than equal to lambda square over n bar square, branching process. But for the branching process, we can compute moments iteratively, right? We just did the calculation for expectation. You can do the similar thing for the square as well, the calculation becomes complicated, so I will not do it. Okay. So, but if you do the calculation, you will see that expectation of nk minus 1 bar squared is like lambda to the power 2k minus 1 over n. So this fact holds. So we will now use this fact to conclude two things that will be important in the proof of the two lemmas that we have. The first thing is, if k is a large but constant quantity, so it does not grow with n, but k is large, say.
Oh, n factors wrong. No, if I plug in these together, then I will have lambda to 2k over n squared. Where am I wrong now?
No, so you have this n, right?
You did it, and then the last quantity, the expectation of n bar square, you just claim that this is lambda to the k minus 1 over n.
Oh, sorry. Okay. Thank you for the correction. This grows in lambda. Thank you so much. That was a mistake.
But again, I think you don't really need those conflicts, right? Because you can just do the classical computer science, the breadth first search, right? So you just take a guy from the queue, expand to the new vertices, and then it takes another one and expands. So don't go like layer by layer, but just go vertex by vertex, and then you just keep going until you discover, say, n to 2 first vertices. And then you have lower bounded is just independent random variables, and they're all the same distribution. And
like
no
all
conflicts.
Yeah.
You never care about those forward edges, whatever computer scientists call them, right? Like you don't have those.
So essentially, those are the same arguments, right? So you need an upper bound, you need a lower bound.
Yes.
So I am trying to make that argument.
Right, but I think there's no need for conflicts. I think that only just makes things complicated.
No, he wants to do that because he later, when he discusses other models, he really doesn't want to one at a time. He really wants to go general.
Yeah, so I will be talking about
GLP, you don't need it at all. Like,
no.
no
So
need for conflict.
this will be related to local weak convergences. Okay.
Cycles. I think you are controlling, in some sense, social cycles, right?
Yeah, exactly. So this will be related to yes.
For that, yeah.
So
Otherwise, you will have
But
a
for
local
GLP, you
coupling.
don't need it at all.
No,
It's
no.
much simpler.
Right, you discard all, right?
Yeah.
No coupling. But then I think he's preparing to show cycles, I think.
It's not cycles, but
That's fine.
so the whole point that I will be trying to make is that if you have locally weakly convergent graph and then you have another additional condition, then you have this concentration of chat. But local weak converges to a branching process. For that, you need to control conflicts. You have a question? Good. So if k is a large constant, the expected number of conflicts is 0, which says the exploration is exactly equal to the branching process with probability tending to 1, right? We can find a coupling such that the exploration would stay exactly same as the branching process up to, say, a finite number of generations. Okay. That's the fact 1 that we'll be using.
No, it's not exactly, it's only in the limit and goes to infinity.
Exactly, but then they have with probability approximately equal to 1. Here you have that n tends to infinity. Okay. We can also take k to be larger. Let's say we grow k with n. We take k equals a log n, where a is less than 1. In that case, lambda to the power k equals n to the power a, right? Because of this logarithm. And therefore, the expected number of conflicts is constant times n to the power 2a minus 1. On the other hand, we know something about branching processes. So we know that the branching process may die out, but when it survives, conditioned on its survival, let's say branching process survives to an R generation where R is large, conditioned on that fact, the further growth of the branching process will be exponential in lambda. So,
So wait,
sure.
because of your notation. It used to be number of vertices. Now you're talking about fraction of the vertices, isn't it? Because lambda to the k. Am I wrong? You know
No,
what I'm
so
saying?
lambda to the power, so expectation of this quantity is lambda to the power k, right? So it concentrates around the expectation when lambda to the power k becomes large.
Yeah.
Okay. So conditioned on the fact that we have explored a lot, conditioned on that, our branching process grows exponentially in lambda. So, and lambda to the power k for such choices of k is n to the power k.
Yeah, sure.
So what is happening? We can compare now these two, right? Now, if a is less than 1, then n to the power 2a minus, well, 2a minus 1 is less than a, if a is less than 1. So the number of conflicts is of smaller order than the number of things you see in the branching process. So therefore, the number of conflicts is small of nk bar with high probability. This says we don't have conflicts. So nk is approximately equal to nk bar. And it grows at lambda to the power k. So the neighborhoods of the exploration process grows exponentially in lambda, right? That's the main thing. Okay, so too many computations, but the thing that I want you to remember from this slide is when we know that the exploration process is surviving, so conditioned on the fact that it has survived for a long time already, conditioned on that, after that, the growth of the exploration process becomes exponential.
What do you mean by long? So that means you have.
There is an iterated limit here. So
This has to do with the L quantity, no?
yeah, it will depend on L.
L, yeah.
But it looks not consistent, so you have to do it.
He's doing a lot of conditioning, I think. Conditioning on good events, conditioning on the other good events. Doesn't matter.
No, but you can't say condition on having survived for long.
Long means, okay, let me make it precise. So there exists an R that depends on L. So, okay, for any given epsilon, there is a, so for any given epsilon, we can choose this. Oh, wait, I think that's a better word. Okay, so for any given L, we know that the component size will be greater than equal to L, right? If that event happens, I want to conclude that the exploration process survives up to some generation R, where R depends on L. And if L goes to infinity, then R will also go to infinity as a function of L. That's what I want to conclude. Okay.
But you always have sent n to infinity before R.
Yeah, we have to send n to infinity before.
And on that slide, you mean exponential in k at the very end, right?
Exponential, yeah, exponential in lambda. So it grows like lambda to the power k.
For k, so
K large enough. K like this.
but is k here a fixed number or growing?
So k is if we take k like log n, then we have this approximation.
Oh, but if what you just all said, you didn't have k growth.
We will again use that, so it will come up. You will see when it comes up. So there is a two neighborhood argument. So for you will see. But
So lambda here is average degree.
lambda is the average.
So what is exponential in average? I mean, I think the branching process expands exponentially a number of steps.
Yes.
But
Well, it is okay. So the conclusion is here, like n to the power k is approximately equal to lambda to the power k.
Right.
That's what I want to conclude.
Yeah.
With high probability, well, will probability which is going to 0.
yeah, I guess I'm just saying nothing is an exponential function of average degree. It's an exponential, you know.
Yes.
The function 2 to the k is exponential in k.
Oh, okay. Yeah. Of course. Right. Well, we have now set up these two ingredients. Now let's prove the next two lemmas. Well, to prove this one, okay, sure.
So what happens in between the two regimes? The constant and logarithmic.
Well, again, it becomes like, if you even take like when the branching process or the exploration has become of size log n, then also if you let this grow with n, then this approximation will tend to hold, right? So because then you will know that already you have survived up to a long time. And if you survive up to a long time, after that, the concentration will be.
C doesn't depend on n. Sorry, C doesn't depend on n.
No, C does not depend on n. It does not depend on any other things. Yeah. Well, we want to prove this. I will just show you this approximation holds in expectation. I will not do the variance computation, right? Because it is significantly more involved. So I'll try to show this in expectation. This proportion of vertices in components, in large components, is approximately zeta lambda. Okay, let's first rewrite this proportion. Let U be a vertex that is uniformly chosen from the graph, and U is independent. U is independent of the graph. Then the proportion of vertices in large components is exactly the probability that this uniformly chosen vertex will land in one of the components that has size at least L. Okay, it's just uniform distribution property. Done nothing funny here. And if U falls in a component of size greater than or equal to L, that means component size of U is greater than or equal to L. Now, in expectation, therefore, we have to calculate this probability. The component size of U is greater than or equal to L. But now we know something. So from previous slide, we know the exploration process starting from any vertex, say U, would be exactly following the branching process with probability tending to 1. So the probability that the component size is greater than or equal to L is approximately equal to probability that the branching process is greater than or equal to L, right? Because these two random variables are growing together. They're exactly same with probability tending to 1. And if we take L to be large enough, this is approximately the probability that the branching process survives.
Subject to your condition on the fact that exploration ran long time enough. So there is a little bit of conditioning going on behind the scene, no? If I want to make it turn this heuristic into a proof, I need this conditional probability, because you said exploration of U is branching process subject to process runs long time enough.
Yes, so L is large, long time enough. For that, I mean L is large, but it is not growing with L. So this approximation has an error, which is going to 0 if you take n tends to infinity, then n tends to infinity.
No, but then if L is large but not growing, then it's not this probability going to 1.
Well, this probability is also going to 1 as you take n tends to infinity, then L tends to infinity. So this, all these approximations are hiding a lot of analysis. I'm hiding a lot of analysis.
Your double tilde is a lot of that behind the scene.
Yes, definitely. But yeah, I just sort of wanted to give the idea what is going on rather than doing the exact analytical calculations. But you are completely right. There are things that is going on behind the scene to make this precise. Okay, so we have arrived at the fact that if you take the expectation of this quantity, that is approximately equal to beta lambda, right? Now, we notice one thing. In the whole proof, the only non-trivial step was this step, right? Whether we can approximate this event by the probability that the branching process is greater than or equal to L. That was the only non-trivial step. So if we were to have another random graph model, say, where we can verify this property, For that, we can prove this lemma, right? The proof is very general.
Wait. You're cheating again. Because you actually need concentration. So now you have to convince us that the second moment as well. And now you have to convince us that if you have two vertices that they sort of potentially far away and independent, so you're hiding a lot of things again.
Right. So that comes up in the variance calculation. But there are some tricks that you can use. For example, you can say that the variance converges to 0 by just looking at local weak convergence. Because, well, this thing is exactly the same as 1 minus sum over Ci over L, where Ci is less than L. Right? Then you can compute the variance.
As long as L is fixed and not concrete.
Yeah. So you can then again take the iterator. Okay. So the important fact here is the local neighborhood starting from U is approximately a branching process with probability tending to 1. Okay. So this is our key fact number 1 that implies the convergence of the proof of first lemma. So this whole theory of approximating local neighborhoods of graphs by some other object, in this case it is the branching process, is called the local weak convergence that I think Christian will be talking about, right? But what this lemma is just a consequence of the fact that the Erdős-Rényi random graphs converges locally weakly to a branching process with high probability. Okay. So far, so good. Let's get to the second lemma. So we can take the squares in the both sides. By the previous lemma, we know that zeta lambda squared is the square of this quantity, right? And we can expand out the square, and the first term is exactly what we have here. So the second term has to go to 0. Right? Now we can again use the same uniform random variable trick, but in this case we have two CIs here, and we have a divided by n squared here. So we will take two uniform random variables now. So we take two uniform random variables, and we again use the same trick to show that the second term is equal to the probability that component size of U1 is greater than equal to L, component size of U2 is greater than equal to L. And there is a funny notation here, U1 is not equal to U2. U1 is not leading to U2. So this means U1 and U2 are not in same component.
Completely, aren't you doing kind of just partially exploring your neighbor? You will stop perhaps when I explore from U1, I see already L vertices, then I think I will stop and then I will explore U2, isn't it? Aren't you doing? It's not the complete component potentially will be in a single largest component. Eventually, if I see all the component, but I think you're doing only partial exploration.
Yeah, so I'm just saying that, well, this is still not partial exploration. In the next step, I'll simplify this event by a partial exploration event.
Because in this notation, if they are not in the same component, in the end of the life, and we know that posteriorly there is a unique largest component. So most of this large component will be eventually one component, right?
Yes, exactly.
By sprinkling whatever the argument you use.
Yes.
This is indeed the kind of a not rigorous.
Well,
doesn't matter. Yeah.
Which one is non-rigorous? This is just a definition.
Yeah, the same component. In what sense not in the same component?
But two components are exactly the same. So this is an event. I'm just writing on the
graph. It just says look at the event.
Part of the graph.
It's just a definition.
Yeah, it's just a definition, right? So how to calculate this event, that's a completely separate thing. But let's say it's a definition. U1 and U2 is not leading to each other. So
Just means they're not in the same component.
Yeah, they are not in the same component. These two components do not intersect. So it is enough to show that probability CU1 greater than equal to 12 and CU2 greater than equal to 12, and U1 and U2 are not in the same component. This probability goes to 0 in the iterated limit, of course. But what this is saying is that if we have two large components, then two large components cannot stay in different components. They should intersect. They have to intersect. Okay. So to show that our event, the probability goes to 0, it suffices to show that probability U1 does not and U2 are not in same component, conditioned on CU1 greater than equal to L, and conditioned on CU2 greater than equal to L is approximately 0. Conditioned on we have two large components, the components should intersect. But now, unfortunately, I mean, conditioning on this event is quite hard. But instead, we will change this event a bit by a different event that leads us to use our exploration process, the tools that we develop for exploration process, right? So we will replace the conditioning event by this event. Let's understand it. Delta RU1 is the number of vertices you have at depth R in the exploration process in each of the exploration from U1 and U2. Okay. Now, I claim that I can replace this conditioning event by the event that the boundary from after exploring from U1 and U2, both of these boundaries are non-zero. Okay, so the exploration has survived up to step R. Now, no, R is not growing. So log L. Yeah, R is log L. That's correct. But R is not growing weekend. R is a function of L. So the basic idea is that if the exploration process is growing, right? If we know that the component size is more than equal to L, that means the exploration process will survive up to a long time, and vice versa. If the exploration process survives up to a long time, then we know component size is greater than equal to L. It's a property of, we can do it for Poissons very easily. Okay. So it is enough to condition on the second event, but when we condition on the second event, we see something interesting happening. The advantage of conditioning on this event is that now we don't have to condition on the rest of the graph, right? So we sort of, this part of the graph in between is completely unexplored. So starting from these two boundaries, we can keep on growing the two neighborhoods. Let's do it precisely more precisely next time. So condition on the two boundaries to be non-empty, and our R is large because L is large. Then recall that we made this observation inwards. After the exploration process survives up to R generation, since R is large, after that the further growth of this exploration process would become exponential. Right? Now, the idea is from these boundaries, we start growing the two neighborhoods in both sides. So we grow the first neighborhood of U1 up to step, say, K1, where K1 is chosen such that, remember that NK1 is approximately equal to lambda to the power K1. So K1 is chosen in such a way that the boundary size is larger than square root n. So after K1, in this side, we have larger than square root n many vertices. We can play the same game on the right-hand side. And after that, grow the second neighborhood and grow it up to U2 until this boundary size becomes of order square root n. Now I claim that after I have done that, it must be that they intersect. Why is that? Well, the probability that there is no edge between the boundaries is 1 minus lambda over n times all possible choices. Omega of n is here.
Said it K1 so that.
Omega n is going to infinity. You can take omega n to the log n or n to the power epsilon, for example.
Now your problem is actually that your first neighborhood, once you have grown it up to the boundary of size square root of n, you can't grow the second one up to that size independently.
Yeah.
So this is again certain.
Yes. So the thing is that if you have to take like large constants, and then if the constants become large, this probability kind of decays. So that's like the argument, but this is simplifying the argument. So you have to take another limit. So as it is to infinity to make it completely analytically precise. But the rough idea is this. So you grow the two neighborhoods up to size square root n, and after some time, they will intersect. When these two neighborhoods have grown to size square root n, then these two neighborhoods have to intersect. That's sort of the idea. Okay. Lot of things, lot of notations, but the main takeaway that you can have from this slide is even if you don't follow this iterated limit and this kind of things, is that if there are two large components, then the exploration process would survive up to a long time. We know that from both of the vertices u1 and u2. And if they survive up to a long time, condition on that, we can grow the neighborhood further. After a long time, the exponential growth rate kicks in. And when the exponential growth rate kicks in, we can grow these two neighborhoods up to size square root n. And when they become large enough, like square root n, at that point, they intersect. Therefore, probability that they don't intersect, that probability goes to 0. Again, n tends to infinity, r tends to infinity. Oh, so that's sort of the takeaway from this slide. So coming back to the proof of the second lemma, we first reduce the proof of the first lemma to the proof of this equation, which says that if we have two large components, then the cannot be in the same component. They have to be in different components. So they have to be in the same component. They are in the different components with probability tending to 0, right? So this is the first condition we simplified. And the second one is, well, dealing with this event was difficult. So we conditioned on the R neighborhood, where R was large. And after that, we started growing the two neighborhoods. So
now all of this only proves that the expectation of this guy is zeta squared of lambda, right?
yes, but you want to show that this expectation, this is going to 0. So you can apply Markov inequality, for example.
No, but how do you prove that this upstairs holds this high probability?
Well, you are taking two limits, right? So you can do. So you want to bound the condition of probability. You apply the Markov inequality and use this. So the approximation
you effectively, when you went from upset to here, you summed over u1 and u2, and you used linearity of expectations. And you can't do that if you wanted to show that the whole thing. So either you have to control the force moment, or you have to give me some other argument why this was an expectation argument, because you summed over u1 and u2.
Yes, but if you want to show that something is going to 0, it's enough to show that the expectation is going to 0. That's what I mean.
Oh, for the cross.
Yeah, it's just the Markov inequality.
Oh, you effectively don't show this, you show the cross terms. And
right,
for that,
right.
you don't need it. Okay.
Right. So what have we found? We have been able to complete the proof of this lemma 2. But the important fact was this again, this fact. Two large components cannot be disjoint. So again, if you have another random graph model where you have this property that two large components cannot be disjoint, then, I mean, modulo some technical conditions, it can be shown that there is a unique giant component, right? So in fact, I will mention a result in the next slide.
Almost a tautology.
Right.
Can't have two large components, then there is either no large component or only one.
But there can be cases, right, where you have like two completely, you are growing graphs in two disjoint vertices. In those cases, you can have two large components.
I think, Christian, imagine a very thin torus, but very thin one, like a ring. Then there might be potentially, if you start from the antipodal points, there might be some two very big components of linear order, but they are not perhaps connected.
Yeah. So
like cutting,
I mean, if you are looking at general graphs, right? This property is not trivial.
Okay, your large here, large really only means.
Yeah, large.
It means, it doesn't mean of order n. Large
Yeah, large here means it is. Well, if you want to bound this probability by epsilon, large means that there exists an L epsilon. That happens. Probability is less than epsilon.
So can I ask a question about the key fact 2? If I just turn my scene differently, perhaps the same thing, same coin, different face or tail, can you then show that there is this connection probability? So U1 is connected to U2, the inf is strictly bounded away from some constant. Can you show such a thing? If components are large. So I give you that, okay, U1 and U2, they lie in a large component, large bounded by this constant number L. And now I want to know what is the lead inf of the connection probability between U1 and U2. This is strictly bounded away from some constant. Then this gives the uniqueness for free of charge, perhaps. What I'm saying? Instead of going through all this.
Yeah, so first of all, we want to replace this event by CU less than.
So it rings a bell because there was this Eindhoven, there was this summer school, and this Holman gave a very excellent talk about this calculation on finite transitive graphs, which is from infinite transitive graphs, and somehow it seems like it's related but not quite. So I'm just wondering whether you have such a kind of a corresponding
so I do not
result.
know about
Okay. You know what I'm saying? If there is a connection probability between 2 points U1 and U2, if they lie, I give you that they lie in a giant large component, not giant but large. But if you guarantee that there is connection probability is always bounded away from some constant lambda.
Look, he can turn this around and say that. So he actually proved.
You have it.
You have it. But I'm talking about not root of n, but
So you don't have it, then it's tending to 0, right? Yeah, the expectation tends to 0, but the probability to 0 tends to 1. Marcus inequality.
So maybe we
So we have to have root of n.
maybe we
Yeah,
should
sorry,
move this
offline,
expert
offline,
discussion to the
offline,
break
yeah,
because I
offline.
think this will be confusing for
Yeah.
people. So are you sort of done with your lecture? Or up to it?
well, I
No,
can
no,
say
no.
about.
You still have 10 minutes.
Still have 10 minutes, so let's summarize. So we considered the supercritical case, right? For Erdős-Rényi random graphs, we proved that the proportion of vertices in the giant is zeta lambda, and the second largest is going to 0. And there were two main ingredients, just to remind you. The first one is local neighborhood approximation. Local neighborhood of a random vertex was a branching process with high probability, and therefore branching process survive if C is large. And we had this nice property that if two components are larger than L, then they must intersect, right? So if we for any random graphs, if we can verify these two quantities, then you can prove this type of result. And we showed this by drawing two neighborhoods, and they must intersect when neighborhoods become large enough, right, of order square root n. Right. So I would refer you to this paper by Van der Hofstad. Again, if you so this paper actually proves that if you have a general sequence of graphs that converge locally weakly to some other infinite graph, and this condition is satisfied, then you always have this theorem. Okay.
Can
Yes.
I ask something?
Sure.
In the subcritical regime, when lambda is smaller than 1, the largest component, if you scale by log n, you have this wonderful formula coming from 1 lambda. And can you say something here as well? C2, if you normalize by log n, then it converges to that particular.
No.
Even if, no, in generality.
In the generality, you cannot say that. These two lemmas will not be related. So that is completely a property of Poisson distribution. Poisson distribution. If you change the distribution, the concentration property changes completely.
But we know that you remove the giant component, what's left is a
Subcritical.
random graph, is subcritical.
Right.
So you know exactly the size of the second largest component.
Yeah, so that happens in the Erdős-Rényi. Yes. Yes, in the Erdős-Rényi, it is true, right? So in the Erdős-Rényi, if you did not follow this proof, you can find different proofs like the one you are saying. You can indeed conclude this is log n. But for general graphs, no.
Well, but morally, okay, so this proof will not give it. But I think morally, okay, if you have, we know that any birth process, okay, actually any birth process, if you condition on extinction, then it decays exponentially. For any distribution. I mean, even with so you have a power law distribution for offspring if you condition on not surviving.
So it has to be branching process, right? The approximation has to be branching process. Right. So what I
but it has nothing to do that it's a Poisson process.
No.
You said it's
well, the I lambda changes, right? If you don't have a Poisson, because that is coming from the rate function, large division rate function of Poisson.
Yeah, different.
You get a different I.
Yeah,
but you still get log n.
So, yeah,
exactly.
For random graphs. So what I said here is, if you have general locally weakly convergent graphs, it is not true that they converge to branching processes, right? But in that case, also this proof holds. This is a very general result. Not only for random graphs. All right, I seem to have 5 minutes. Let me quickly tell you about another useful application of the technique that we learned, but in the context of typical distances in Erdős-Rényi, we will use similar ideas, but be quick about the proofs, right? So typical distances, what is it? It is a graph distance between two uniformly chosen vertices. So you take two vertices, U1 and U2, you look at the shortest path and how many edges are there in between. Then in lambda more than one case, you have that the distances scale like log n. Distances divided by log n converges in probability to 1. And again, the proof uses this neighborhood growth idea, right? So we can again use the same neighborhood growth idea. We can grow the two neighborhoods, and we saw that conflicts are small and they have disjoint boundaries until their size is square root n. So until their size have become square root n, these boundaries remain disjoint. So there is no shortest path between U1 and U2, but at half log n, the shortest path is created, right? So the shortest path will be created when these two neighborhoods intersect for the first time. And that happens when you take k equals log n plus something, okay? So if you take k equals log n plus something, half log n plus something, then these two neighborhoods will again intersect. And we will find the shortest path. So what I'm saying here is the distance between U1 and U2 is the size of the boundaries of the two neighborhoods that we have grown plus a small correction, right? And therefore, the distance is approximately equal to log n.
This was only a lower.
Yes, but so I have said that they will intersect, right, after this step. So that gives an upper bound.
How do you put the lower bound? Sorry.
So lower bound is what the fact that they do not intersect up to square root n. That's a lower bound. An upper bound is they will intersect. All right. I think this is a good place to stop. Next day, I will tell you about more random graph models and apply this technique that we have learned. Okay. Yeah. Please let me know if you have questions.
You did this typical distance. Sorry. The worst case distance, not that U1, U2 are uniformly chosen.
But in that case, what it happens is that in the giant component, there are some hanging trees as well. They behave like subcritical trees. So you have to take into account their distances as well. So the diameter is not log n, but there is a constant, additive constant in front of the log n. The 1 plus some mu, where mu is actually the survival. It is related to the survival probability of the complemented branching process. Condition on is not survival.
I think this is pretty complicated, right?
Yeah.
This is
Yeah.
It is. I was just wondering
I don't
because
even know it's that. Is it really known? It's
Yeah, this node.
Function
Yes.
is a result. But what I wanted to ask is because we are turning, so instead of the very much combinatorial counting argument, which we usually do, because of probabilist, you are putting the things in a more general box, and it seems to be very, very nice. So that's why I'm asking if you want to have such an extremal quantity, whether you have also a kind of result using max. If you know that some uniformity, is there any trick to have a maximum thing using other probabilistic tricks? That's all right, what I want to know.
So in probabilistic tricks, in terms of probabilistic tricks, what you have to use is there can be hanging subcritical trees that is not taken care of in typical distances. And what is the distances in subcritical trees? So you have to add that here.
Yeah, that's for me combinatorial.
So that's
I already know the
combinatorial?
structure. We don't know the structure. We already know it's kind of posterior, right? Because we know how the giant component looks like, you know, two core and trees, whatever. So it's kind of, without knowing that, such an intuition would not work. That's why I'm asking, is there any more high level probabilistic argument? I do know something about the uniform thing. If I choose like a random walk, if I start from a uniform vertex, then mixing time will be something. But if I look at the worst case mixing time, if I start from anywhere, the worst case can be much larger. Universal kind of a nice envelope.
I do not know about any such
There might be
universal.
some. Yeah, thank you.
But you can actually get diameters for random graph models like configuration model or say, of course, in Erdős-Rényi random graphs. And in that case, what happens is you get this additive constant that comes from subcritical branching processes because they can be attached to the giant component. They are there. And they can make the distances large of logarithmic order actually.
Yeah, question for this. You mentioned there's some general results that can look at the largest giant component. So what is the general model? How general?
So it is very general. So it says that if you have a locally weakly convergent sequence of graphs, and the zeta lambda is the probability that this graph is infinity, graph is infinite, then with this local weak convergence and this additional condition, you can show this property. There is a unique check.
Does that cover random regular graph?
Yeah.
Yeah.
So then that will be 1. Okay, yeah. So
That would be 1,
yeah.
but you still have not verified this one. I mean, yeah, you can actually verify this condition for configuration models. Yeah, again, argument is a bit complicated, but you can do it.
Okay. I think we deserve a break, so let's break until 11. Then we'll have different topic than we have epidemics.